In this video, we are continuing our discussion of numerical differentiation. And in particular, we're going to talk about the concept of calculating derivatives using interpolation functions. So the basic and high accuracy formulas that were derived in the previous sections were based on equally spaced data. So the distance between the points xi minus 2, xi minus 1, etc. was constant and typically referred to as h. It should be noted that it is possible to derive formulas for unequally spaced data, but in this case the derivatives would be functions of the spacings close to xi. Additionally, we can fit a piecewise interpolation function of a particular order to the data and then calculate its derivatives as discussed in Chapter 8. So this technique provides a better estimate for higher values of h. However, the disadvantage is that depending on the order of the interpolation function, higher derivatives are not always available. So first let's talk about first-order interpolation, where we fit a linear function between each of our subintervals or each of our data points. So in these figures, the blue solid line is the actual function and its derivatives, and again we're considering the Runge function. The orange solid line is the piecewise interpolation function and its derivatives, and the black dots are the values of the function and the derivatives at the sampled points. So for the first order interpolation, we can see that the first derivatives are exactly similar to the results using the forward finite difference technique. We can also see that the second derivatives and higher are equal to 0 everywhere. And this is using first order interpolation with different values for the h. So using a higher value of h in this first column and a much smaller value of h in the second column. So you can see when we increase the value of h, the first derivative, we get a very nice approximation of the first derivative, but for the second derivative and higher, we cannot get an approximation as the derivative values are 0 everywhere. And that's because the order of our spline that we're using is just is linear, so when we can take one derivative, but we can't take derivatives beyond that. They are all equal to 0. So second order interpolation provides a much better results for when h is less than 0.1, for example, in this case here, compared with the finite difference formulas. So if you look at, this is the first derivative here and the second derivative here, and we get actually a very good approximation of the derivatives. However, the third and fourth derivatives are both equal to 0 everywhere, because again, here we're using a second order interpolation function, so we can only have two non-zero derivatives. And if you compare the results for the first and second order, in particular, the second derivative with the finite difference approximations from the previous section, you'll see that we get much better results using this interpolation function compared to the finite difference approximations. Using third order interpolation or cubic splines, we get much better results even for h up to even 0.2 compared with the finite difference formulas. And this is for all of the derivatives up to the third one, but the fourth derivative is equal to 0 because we're using only a third order interpolation function.